Okay, good morning. Welcome back to our lectures on optimization and dynamics. So today we're just going to extend on the mind map that we looked at last week, just perhaps a quick review of what we discussed. So we started off just with a quick review as well of the DAP-BC workbench. We mentioned that it's a general purpose workbench, which makes it ideal for integration with some sort of an optimization technique if we want to do design studies. The fact that it's a numerical approach and we're not limited by user interface means that we can also easily adapt the MATLAB scripts that we have available to include that optimizer. And the optimization that we looked at was the dynamic queue optimizer. We mentioned that this is a gradient-based optimizer, so it makes use of the objective functions gradient as well as your gradient vectors and matrices for your inequality and equality constraints. And on that note, we also mentioned that the dynamic queue method basically breaks up any lower and upper bounds from regular inequality constraints. If we have some sort of a non-linear inequality constraint, then we denote that by this G subscript J, and we can evaluate that differently to these lower and upper bounds. So the lower and upper bounds are simply linearized versions of inequality constraints, so we can solve them much easier. So with that in mind, we then looked at the optimization only examples, and these were about 3 examples or so, fairly easy in the sense that we had the analytical functions available, so we could easily go and check whether the optimization that we performed does give us the correct values or the correct minima. Then we specifically focused on example problem 3 as well, and this one is now a multi-variable problem. So in this case, we have 4 variables, and this is now where it becomes a bit more or less trivial to solve these type of problems. We can't really produce a graph for these problems, so instead we need to rely on something like a dynamic queue optimizer or any other type of optimization technique to solve these problems. Then we also looked at the general formulation of gradient vectors, and these are generally applicable when you have some sort of an analytical function. If you don't have an analytical function available, then we tend to rather resort to some sort of a finite difference method. And the one that is proposed for the dynamic queue optimizer is simply the forward difference method. You can also use the backward difference method or then the central difference method. The problem with the central difference method, however, is that it's basically a combination of a forward and backward difference method. So it's going to take longer time to actually solve the problem. All right, so then we also focused our attention to a few applications that we can look at for the dynamic queue DAP-BC hybrid workbench. So these examples, one of them included the length and rotational acceleration of a driven pendulum that we perhaps want to vary so that we can perhaps minimize something or maximize something like the acceleration of the system. So to do that, we're going to look at that pendulum rod example today. But before we jump into that, we're just going to extend the optimization procedure that we previously looked at under section 3. And this is now just for the integration with the DAP-BC. So the DAP-BC workbench should first and foremost be updated to not need any inputs during the process. We know if we just run the DAP-BC, we need to give the folder in which we have all of our input files. We need to state the final time, the reporting time step, all of those things. So when you perform the optimization, you don't want to continuously give this as input. You instead just want to specify it at the start of the optimization and then run the optimizer and see what happens during each iteration. So the following fundamental changes can then be made to the DAP-BC workbench or its MATLAB files. Firstly, under the dap.m script, we want to manually insert the folder name containing the input files so that the system does not ask for this each time the optimization runs in iteration. And the example that we're going to look at today is the pendulum rod D, so it's PR_D. What we essentially just do is we go over to our DAP-BC workbench, or in this case, it's going to be the DAP-BC dynamic queue hybrid workbench. So this one already has those changes made, so you don't have to worry about that, but it's just important to understand where these changes are being made. Okay, so firstly, we have in line 16 of the dap.m file, we had this folder equal to input, which folder contains the model. And this is the line that we just want to comment out. underneath that, we're then going to specify folder equal to pr_d. So we now directly give it the folder name as input. Once that is done, we also want to comment out the initial condition corrector input line as and define it as on equal to y. And this will ensure that an initial condition correction is always performed, which is a good practice for complex multi-body systems, just to make sure that you have continuity in your system. So if I then go down, you will see this is now in line 24. So I commented this line up, which says answer equal to input. Do you want to correct the initial conditions? And underneath that, I simply say answer is equal to y. And that then also gives it direct input into the dap.m file. Then still under the dap.m file, we want to manually input the final time and the time step values. And the example that we're going to look at as well, these reporting time step and final time values are given as 3 seconds and 0.001 seconds. So I just also manually added this to the dap.m file. So this is in line 39 and line 46. Once that is done, we also comment out the last 2 lines in dap.m to suppress the display of the number of function evaluations. So you'll remember if we run this problem, then it basically prints out the number of function evaluations, or it gives you a number as it steps through the iterative dynamics. And if we suppress this, then we just make sure that once the iterations are going to be printed out to the screen, then you're not going to have a single iteration, have a bunch of function evaluations next iteration. You just want everything, all the iterations below one another. And then once that is done, we also just want to comment out the corrected initial conditions output under the formulation analysis IC_correct.m script. So to find this one, we just go over here to this subfolder formulation. We expand that, and then you should see this analysis folder over there as well. And we just head to IC_correct over here. And you'll see these are the last few lines that we have over here. So I think it's the last 7 or 8 lines that we have that you just want to comment out as well. Now the question might be, how are you then going to validate that you get the correct initial conditions after correction? My suggestion would be, before you go into some sort of an optimization study, to first just do an initial design and then still print out the corrected coordinates, see if the corrected coordinates match what you expect to get out. And then once that's correct, then you can suppress this and you can run through your optimization, and then once again just do a quick validation on the final design as well. All right, so that's more or less all of the changes that we wanted to make under the dap.bc MATLAB script. So then we have a second procedure over here, which provides a guideline on how to adapt the dap.bc dynamic queue workbench to solve these dynamic problems. And what we first want to start off with, and this is also in line with the original procedure that we had for those analytical functions, we first want to identify the parameters that we want to minimize or maximize, and this will define your objective function. Once this is done, we identify the parameters that will influence the optimization, and these are simply your design variables. Now, step 3 is important in the sense that you just need to understand when to use which naming convention. Whenever you're working with the dap.bc MATLAB input files, if you assign a design variable to one of those files, you need to name them x_dap and then give the index number in brackets as well. So xdap1, xdap2 up to xdapn for in design variables. Then we want to make sure the vector xdap is defined globally under the formulation. Some files include global.m script as well. And this is found once again under formulation. If you go over here, you'll see there's a sum files subfolder. So you're just going in over there, and then you're going to click on include global. And you'll see in this case, I've already included it. So it says global x_dap. And this just makes sure that when you work across different MATLAB scripts, that xdap is carried over to those different scripts. All right, then for step 5, we want to define any constraints, whether it be inequality, equality, or boundary conditions that may be imposed on the data or the variables. We also define a new script and function which takes in the relevant design variables and outputs the function and constraint values. So essentially we want some sort of a transition script where we, for example, let's say we want to get the actuator forces from the DAP study. Then we're going to use that function or that subscript to basically get out the force values, get out any inequality constraint values, and then we're going to transfer that over to the dynamic queue files. So that then follows to step 7. Under the dynamic queue folder, we update fch.m to obtain the function values from the new script in point 6. Under grad fch, we just make use of some finite difference approach to define the gradients. And over here, they also refer to this delt x that we might need to change. So if we quickly go back to the dynamic queue subfolder, under grad fch, you'll see that you have the central difference method is over here. We're going to rather rely on the forward difference method. And you'll see over here, there's delt x equal to 1.d minus 8. So this is essentially 10 to the power of minus 8. This is a value that is usually determined via some sort of a sensitivity analysis. And it's more in line with, I'd say, the optimum design module. So we're not going to ask you to perform a sensitivity analysis in MSD 780. Instead, if you have to change this value from 10 to the power of minus 8 to something else, we'll give you that different value that you have to change it to. All right, then step 9 is in the main folder. We want to update the optimization.m script to include any starting points, lower and upper boundary conditions, and any other inputs that are not at default. And this is now an additional script that we also added to the DAP-BC dynamic queue hybrid workbench. So if you go to optimization.m, you'll see that over here you have more or less a structure of what you need to define over here. So we once again add this add path, gen path, dynamic queue. You'll see this is also something that is added in the MATLAB scripts, or yeah, I think it's added in the MATLAB script, but this just makes sure that since you're working in a subfolder, we extract those scripts that we have under dynamic queue to this global folder over here, and then we can utilize it. So in this case, we also just say include global to make sure that we carry over any global variables. And then we define our design variable values over here. So this is x1 up to x4. We have our x0, which just combines all of these initial design parameters. And then we also have our lower and upper bounds. And over here, we simply run the dynamic queue optimizer with the suitable inputs as well. Okay, and then if you're interested in the runtime as well, over here, we just added the time print as well. So this just tells you in minutes how long the optimization is going to run. Okay, so once that is done, we can simply execute the optimization.m script and wait for it to run. Depending on the number of variables, dynamic complexity, and the initial values, the computational time and effort is going to vary. We saw this previously with section 3 as well. The more intricate your analytical functions got, the more time or the more iterations it took to solve the problem as well. All right, so this is, I think, yeah, more or less the optimization procedures that we're going to look at. So are there any questions at this stage? Right. Just want to see under the chat messages. Okay. All right, so then we can move on to section 6, and this is now an application example that we're going to look at, and more specifically, the driven pendulum rod that is subjected to a constant torque. And this is previously the PR_D pendulum rod example that we looked at. So it's a fairly simple example. We have a single body mechanism, and we perhaps want to ask some design questions over there. So just to quickly review what this looked like, we essentially had this 0.6 meter long pendulum rod over here. Its local coordinate system oriented with the x-axis in line with the longitudinal axis of this pendulum rod. And then at the revolute joint over here, we also specified the global coordinate system. So we only consist, or our system only consists of a single revolute joint over here, and then our single body mechanism over here as well. Point 3 as well was not necessary to define, but it's useful if you want to just simulate or animate what happens to this pendulum rod as it moves. So the forward dynamics problem, we proposed a torque and measured the kinematics, so the acceleration and the velocity. And this is essentially the free body diagram that we considered for that. We had some input torque defined over here called N. And then we just had all of the acceleration or the kinematic properties as well that we defined. So we can now expand on this problem by asking some fairly simple design questions. Firstly, what is the maximum reasonable acceleration the pendulum rod can achieve? How does the initial orientation of the rod influence this value? What is the influence of the constant torque on the acceleration? And what would happen if we vary the mass of the system? And lastly, how does the pendulum length influence the kinematics? And these are all design questions which can be investigated simultaneously using the dynamic Q optimizer. So using these questions, we can now formulate a design problem. And this is simply given over here. So we want to maximize the acceleration of the pendulum body. In this case, we can assume that the acceleration is the linear acceleration that we're talking about. So of the pendulum body 1, subject to the starting angle, phi 1, the torque that we specify, which is N, the mass of the rod M1, as well as the length of the rod, which we're going to denote as L. And then we also have some design considerations over here, and this will guide us in terms of any boundary conditions or constraints that we have. So firstly, they say the maximum time over which the acceleration may occur is 3 seconds, and we want to use a reporting time step of 1 millisecond. The starting angle may vary between minus pi and pi. The torque may vary between 3 and 10 Newton meters. The mass of the pendulum rod should be between 2 and 4 kilograms. And then we also have the moment of inertia that should remain unchanged at 1 over 12 ml square equal to 0.06 kilogram meter square. Now it's important to just notice that this moment of inertia that you specify over here, it's actually a function of two of the variables that we have over here, the mass of the rod as well as the length of the rod. So we just need to take this into account when we specify our inequality constraints or equality constraints. And then lastly, the maximum velocity magnitude, or simply the speed, should be equal to 20 meters per second. Okay, so with all of this defined, we can then follow the optimization procedure to set up the optimization problem in the dynamic queue and the DAP-BC subfolders. So if I go over here to step 1, firstly we need to define our objective function, and we define this under the post.m file at the end, and this just makes it a bit easier to extract once we go over to that transition script later on. So rather define it under post.m, and then you can just call this variable when you want to send it over to the dynamic queue script. Okay, so in this case, it's the objective function that we're looking at is the linear acceleration of the pendulum. So I'm just going to calculate this, and I'm going to name it max underscore ACC underscore val. And this is then simply equal to the square root of the x acceleration squared plus the y acceleration squared. But just to show you where I specified this, if I go to the post.m script over here, you'll see that this line 66 that I have over here specifies that function over here. So now we have our objective function value calculated under the DAP-BC folders, or the DAP-BC scripts. We can ignore this max speed val for now. We're going to get to that in a moment. But once that is done, we then want to go and identify the design variables, and we also want to assign an index to each of these variables. And just looking at what we specified initially, we said that it's the starting angle, the torque, the mass of the rod, as well as the length of the rod. So I just grouped all of this together in this design variable vector. So x1 is then the starting angle, phi 1. x2 is the torque that we applied to this pendulum rod. x3 is then the mass of the pendulum rod. And x4 is the length of that rod. Okay, so once that is done, then we just need to go and define these design variables in DAP-BC. Now, I know that the mass and the length properties are used within the in-bodies file, so I'm going to start off with that in-bodies input file. So if I go back over here, I just need to remember that I'm now working under models, and I did update my dap.m file as well over here to say pr_d, so that's fine. So if I now head to pr_d in-bodies.m, the first thing that I need to look at is the mass of this pendulum rod. So that is now b1.m is equal to x_dap3. X_dap in the sense that I'm working under my dap-bc files. So I use this naming convention. And then 3 corresponds to the index that I use over here. So x3 is equal to m1. Once that is done, then I also need to remember to update this J value over here, so the mass moment of inertia. And that is then given over here, b1.j is equal to 1/12. The mass is x_dap3 multiplied by the length, which is x_dap4, and I just square that one. So this corresponds to the function that I gave over here. Okay, so with that done, then I also need to specify the starting angle. So b1.p is equal to x_dap1. This is also a design variable. And this then corresponds to x1 that we have over here. So x1 is equal to phi1. And for the initial coordinates as well, these are going to depend on the length of the system as well as the starting angle. So this is simply what I introduce over here. So I say that I just give a trigonometric function over there to calculate it. If we go back and we perhaps look at, I think this one would be best. So you have L/2, L/2. So in other words, the location of this center of mass is going to be L/2 cosine phi1. And then its y coordinate is going to be L/2 sine phi1. So this is simply what I add over here. So x_dap4 is L, and then x_dap1 is phi1. So that is then everything that I wanted to specify under the in-bodies file. So then I can move on to the next input file that I have to change, and that is in forces. And over here, if I go to in forces, then previously I had some sort of a constant torque value that I specified over here for S2. In this case, I now know that it's going to be a design variable. So over here, I now need to just update this to say x_dap2 with x_dap2 corresponding to the torque. Once that is done, I just have to go over to endpoints as well. And this makes sense that I need to update something under endpoints, because if I have the so if I have my center of mass over here and the length of this system changes, then it means that the distance to 0.1 is also going to change. The distance to 0.3 is also going to change. And to then illustrate this, if I go to endpoints, 0.1 is not going to change. This is on ground, and it's at the global coordinate system. So the global coordinates origin, so it's just 0, 0. But 0.2 and 3 are going to update. So 0.2 is located minus L/2, and then 0.3 is located L/2. Okay, and I can just check that that also corresponds to what I have over here. 0.2 is situated over here, 0.3 is situated over here. So from the center of mass, it's going to be minus L/2 and L/2. So that's fine. Okay, then for step 4, we just need to make sure that x_dap is defined globally under the include global file as well. And I can quickly just go and check that. So if I go formulation, some files include global, I can see that x_dap is still defined, so that is correct. Then I can go and define the constraint functions required to limit the design parameters. And this is, firstly, I just want to look at the maximum velocity magnitude, since this is a value that I get out from the dap-bc. So the speed is defined in the post.m script as max speed val, equal to the square root, and once again it's the x velocity squared plus the y velocity squared. And this is now what I specified under, I think it's the post.m script over here. So this max speed val in line 67. For the other general formulations that I have over here, I just need to say that h1 is then equal to v1 max, so the maximum speed minus 20. So this corresponds to what I said over here. Maximum velocity magnitude should equal 20 meters per second. So I can set up an equality constraint from this. Okay, and that is then h1 that I have. h2 is then 1 over 12 x3 times x4 squared. So this is now the inequality or the equality constraint that I'm looking for. In this case, this j over here. So I just take over the minus 0.06 so that everything is equal to 0. And once I do that, I get this function over here. Then I also need to just define my lower and upper boundary conditions. So I just group all of this together in the correct vector form. So we have on variables 1, 2, and 3, we have lower bounds, and then we also have upper bounds on those variables. Okay, then I need to go over and look at minimizer inputs, and this is now the transition script that we talked about previously. So we now define all of the necessary properties under the post.m file, and we updated our design variables under the DAP-BC input files. Now we need to go to minimizer inputs, and we essentially create a function over here called minimizer inputs that takes in the variables that we want to specify, and it outputs the objective function and any inequality or equality constraints that are of interest. Now if I go to the global folder again and I head to minimizer inputs.m, you'll see that that is what I specify over here. So once again, I just start off with add path, gen path formulation. I include all my global variables over here. And then since I used val over here as the input argument, I'm just going to set xdap equal to val in this case. And what you'll notice is that if we were to directly use val in the DAP and the post files, you would have a problem where you first specify the variable and then you globalize that variable. And Octave usually gives you some sort of a warning when it performs that. It's not necessarily going to crash or not give you the correct answer, but it's just good practice to make sure that before I assign a value to xdap, I first need to globalize that variable. And that is essentially what I'm doing over here. So I just say xdap is then equal to that input value over here, or input vector. Now I can run the DAP and the post scripts to essentially run the iteration for the x variables that I chose. Once I've done that, then I can go and extract the objective function. In this case, it's minus maximum acceleration value. And that is because I want to maximize the acceleration of the system. So to turn a maximization problem into a minimization problem, I simply multiply by -1. And then I also specified h1 over here, which is equal to the max speed value minus 20.0. And you'll notice that over here I didn't specify h2. We're going to look at that under the fch.m file. So I can in fact specify any equality constraints that are explicitly given in terms of the design variables. I can directly specify that under the fch.m file. But in this case, since I'm calculating the maximum speed value under this post file, I rather want to include this equality constraint over here. Okay, so that is then the transition file that we have over there. Then I want to go and call the minimizer function in the fch.m file to obtain values for the constraints and the objective function. Okay, and this is now given over here. If I go back to dynamic queue, then I'm still going to work in the main folder, but I just want to open fch.m over here. Okay, and in this case, so it's not been programmed in yet. So what I'm just going to do is delete what we had previously. Okay, so what I'm going to start off with is just say f and h1. And I think I just want to check with minimizer inputs. Okay, so I did use a comma, so I'm just going to include a comma between F and H1 as well. And then over here, I can now say it's equal to minimizer inputs. And now I'm just going to use X. And I'm not using XDAP over here since I'm now working in the dynamic queue folder. So whenever I'm working in this folder, I just use X to denote my design variables. So with that now being defined, I just need to make sure that I use the correct indexing for my equality constraints as well. So I'm just going to now say H in brackets 1 is equal to that H1 value that I got. And then I can now go and specify H2 as well. So H2 we said is 1 over 12 times x3, so that's the mass, multiplied by x4 squared minus 0.06. Okay, so now I've defined the objective function over here. I've defined H1 and H2. So that should then be fine. So I can just save this script over here. Then for step 8, I need to use the forward difference method to evaluate any gradients under grad fch.m, and we want to use a delt x value of 10 to the power of minus 8, and this is deemed appropriate for this problem. To do that, I'm just going to head over to grad fch. Right, and I'm going to just unsuppress this code over here. And I can just hide this as well. Okay, so I'm using delt x equal to 1.d minus 8, so that is 10 to the power of minus 8. All of the rest of the properties are more or less stock standard, so if you don't have any inequality constraints, for example, then it in any case doesn't calculate that. Yeah, so that should then be fine. And GH, we do have equality constraints over here, so that will calculate it accordingly. And all of the other properties are calculated in accordance with the forward difference method. Right, so now that that is done, we can go to step 9, and this is now update the optimization.m file in the main folder. And this is used to define the boundary conditions, chosen starting points, and any other non-default inputs. Okay, and they didn't specify it, but I see over here we now have a different value for X tolerance. So the convergence tolerance over here on the step size is set to 10 to the power of minus 3. If I go over there, yeah, so it's this one over here. So essentially I'm just specifying all of the starting conditions over here. This wasn't specified in the problem itself, but it's just given over here nonetheless. So I start off with a starting angle of minus pi over 6. X2 is then the torque that I specify, that is 7. X3 is the mass as 1 kilogram. And then X4 is 0.2 meters. Then I just group all of that together in X0. The lower and upper bounds are also given in accordance with the specification that I had previously. So this one over here, I'm simply just translating this to the octave fields, or the octave version of these matrices. Once that is done, then I can go and run this xf equal to din q, x0, which is my initial point, lower bounds, upper bounds, and now I use a move limit of 1, so this should be fine. 10 to the power of minus 3 on the x tolerance, and then 10 to the power of minus 8 on the objective function tolerance. I'm just going to use runtime then to also check what the total optimization runtime is. And once all of that is done, I can go to step 10, and this will be the optimization.m that I execute. And I just want to go and check what the results are going to be. So if I do that, I can head to my command window and just say optimization. Okay, so this is a bit of a long problem to run. I don't think we want to wait 46 minutes for this one to run. But yeah, so you'll basically end up, but you can go and run this at home as well and see if it works. But it should, and what you're going to end up with is it's going to be 23 iterations that it's going to take. At the end, you're going to get a value of minus 1,887 for your acceleration value. Now, this value that you get over here, you just have to go and multiply by -1 again. That will then give you the actual maximum value. We can see that on the X norm, it now terminated. So it terminated on the step size with a value of 8 times 10 to the power of -4. So it's smaller than 10 to the power of -3, which is fine. And then it also gives us the optimum design variables that we found. So in this case, it's 0.179 on the starting angle. You can go and convert this as well to degrees. It will probably be a bit more representative of what's going to happen to the system. Then 8.94 Newton meters on the torque. Then you also have 4 kilograms for the pendulum rod mass. And then lastly, you have optimized length of 0.424 meters. And then you'll also notice over here the constraint values are given. So in both cases, we can see that it's fairly close to 0. 10 to the power of -2, and then H2 is 10 to the power of -6. And then we also have our side or boundary conditions. So all of them are negative, which is good. So that shows that everything is met well. CX3 is just 10 to the power of -6. So once again, very close to 0. Since we're working with smaller than or equal to 0, this 10 to the power of -6 is fine. And then the fact that I used, in this case, XF equal to this line over here means I can directly extract the optimum design variable and the optimized objective function as well. So I simply type in X, and what I get is these design variables over here. And then F will be minus 1,888, which I just have to multiply by -1 to get the acceleration. Right, I'm just going to, we'll just see if it runs for...
If you remove one of your design functions, wouldn't you see like the drastic improvement in the runtime?
I don't think so, no. So with these type of problems, it more depends on the actual dynamic analysis that's being performed. So even if you use some sort of a constant value, the dynamic analysis will probably take a while to run. I think in this case, the number of function evaluations that it printed over here is 51,600, which is quite a lot. So I think it's more, in this case, it's more dependent on the actual dynamic analysis rather than the, rather than the actual number of variables that you use. Yes. Yeah. Okay. And then, no. We usually, what we do is it will take about 5 to 10 minutes, I'd say, at the most. We did one last year as well, where we gave the students essentially like the input functions and stuff, and it ran fairly quickly. So usually, if it runs like for more than, I'd say, 15 minutes, then it means there's probably some problem somewhere that you just have to go and reevaluate. Yeah. Right. So finally, we can also just look at the graphical results that we're going to get. So once the optimization has completed, we can just go and group up all of our optimum design variables. So this is essentially what I did over here. And now you'll see the angle that we proposed previously, this 0.179. If I relate that to degrees, then it's 10.25 degrees. Then T, the torque is also given, mass and the length. I just group all of this together. And now I can go and look at the maximized acceleration as well. I just want to see, so this is plotted as a function of time. So once you are done with the optimization, then what you can do is basically just populate your original MATLAB script files with the optimized values. And then you can go and run the post script again, and you can go and check what the acceleration is as a function of time. And over here, we can see this sort of oscillatory behavior over here, up to about that 1,890 that we saw. But the more important one, or the one that we can actually gauge whether correctly stated, the equality constraint is the velocity magnitude, or then the speed. So we can see the system starts at 0, then it has this oscillatory curvature over here again, and then at 20 meters per second, after 3 seconds, it now stopped. Okay, and this is what we expect. We said that the maximum allowable speed has to be 20 meters per second. And lastly, we can also just look at the initial configuration and the orientation of the pendulum rod. So this is given over here. So this angle is then your 10.25 degrees that you have. Okay, so I think that then more or less wraps up the example that we wanted to look at for today. I just want to see if this one still runs. Okay, so somewhere I forgot to turn off the function evaluations. I just want to see if it's, yeah. So I just have to suppress this, and you'll now see that since I didn't turn it off, what happens is you have these number of function evaluations that are going to print out. Then you're going to have iteration 0. It's going to give the data, and then a bunch of function evaluations as well. Now, what is interesting to note as well, if I now didn't terminate it, you'll actually see that depending on your depending on your number of variables. So I guess the number of variables does have an impact, but more from a gradient perspective. Since you're working now with the forward difference method, what essentially happens is that for each gradient calculation, or for each design variable that you specify, an objective function at the step size needs to be determined as well. So if you have 4 design variables, then 5 function calculations are going to be performed for that iteration. So one function evaluation is going to be at that value of the design variable, and then the other 4 will be x1 plus 10 to the power of minus 8, x2 plus 10 to the power of minus 8. So it's just to calculate those localized gradients in each direction. So it is going to have an effect, but I think primarily the thing that influences something like this is most likely your number of function evaluations that you have for your actual dynamic analysis. Yes.
How many times did it run the optimization iteration twice, so that the gradient and next?
Yes. Yeah. So
shouldn't it have then displayed the iteration value for the first step of those 2 function evaluations then?
So what it does is it first calculates the gradients, and then it prints out the iteration. So it could have, you could have had iteration 0 printed out first, or iteration 1 printed out first, and then it performs its gradients. But it essentially does that. So it does calculate, because you specify, I think if we go back to grad FCH as well, so it's not going to calculate between 2 consecutive design variables that it chose. It's just going to calculate at the initial design variable that you specify, and then it's going to take a plus 1 times 10 to the power of minus 8 step to the right, and then it's going to calculate the gradient over there. And that basically guides it from a localized perspective in which direction it needs to move for iteration 1 and iteration 2 and so forth. Yeah.
But with regards to the results that it runs,
yes.
How many times does it run to create a data with what prints the next set of results?
So it will run 5 times. In our case, it will run 5 times because you have 4 design variables plus then so it calculates the gradient for each of these. So x1, x2, x3, x4, and then it calculates at the design variable value itself as well. So to perhaps illustrate that, I wonder if you just see if I can maybe draw this paint. Okay, so what happens is, let's say I have my function that I plot over here, and this is now a bunch of data points that I get some sort of a curvature like this for. If I'm testing x1, so if this is x1 over here, then I'm going to have my objective function value over here. So the objective function in this case is the maximum acceleration. I get that from the DAP BC. So in order to get the objective function value, it needs to do 1 run of the DAP BC. Now, if I look at x1, and let's say x1 is now specified over here, then it's going to calculate the objective function. So over here, it ran DAP BC once. but now it also needs to determine the gradient. So what's going to happen is then, let's say it calculates over here. At this point, this value is going to be x1 plus 10 to the power of minus 8. So a very small localized gradient. And then it uses this to calculate the linear gradient over here. And now it sees, okay, it's decreasing in this direction. So I'm going to move in this direction, and let's say the next point that it's going to select is going to be over here. And this will then be x1 at iteration I equal to 1. Yeah. Right, so the fact that we're using localized gradients means that it doesn't have to run 2 iterations before it gets information about the next iteration. Yeah.
And that's why I like to run part of the baseline and then evaluate each design.
Yes. Yes, that's correct. Yeah. All right, so I think that more or less then wraps up everything that we wanted to look at for this example. Yeah, so I'm not going to do another example today. I think, I think we'll we'll continue with the next application example in our final theory lecture. After the next lecture, we still have 2 lectures left. My suggestion is that we perhaps work through a previous exam, I think last year's exam, just to see how the optimization is going to work over there and how to set up the dynamics at that point as well. But yeah, this is then everything for today. I just want to check if there are any questions under the chat messages. Okay, so I think we're good. All right, so then I'll see you again next week. Thanks.